Hello, my name is Werner Keil. I'm an Eclipse Babel language champion, Jakarta EE specification committee member, and active contributor to several Eclipse projects. Together with Ahmad, Seko, and Oliver from the German BFR and IBM, I'm going to tell you about Eclipse STEM today and how it can help save the world from the coronavirus, Ebola, or other infectious diseases. Here's our outline. So I'm going to do the introduction part. Then Seko and Oliver will tell you about disease models and show you a live demo of STEM. And Ahmed will show the next generation of STEM, STEM 5, in the web. In Dan Brown's thriller and movie, Robert Langdon, played by Tom Hanks, had to race across southern Europe trying to prevent the spread of a very infectious new disease that threatened to wipe out a large portion of the world's population in less than a week. As a coincidence, earlier this year, not that far from the filming locations in Italy, especially in the northern part, people were most affected, and Italy was one of the worst affected places in the world. Over 40,000 people have died there so far, and this is a scene from the peak of the infection so far, where even the military had to carry away dead people, almost like in a war scene. To model such disease outbreaks, you need a framework that has information about humans and other species, infectious diseases, and vectors like insects or other types of infection, and also food that people eat in some cases. For example, the so-called mad cow disease that was spread from eating meat. It takes a large community, unlike some country and their rulers who think working on their own is better. Eclipse and Eclipse STEM are the result of an international collaboration. So as you can see, in this case, even Mexico paid for it. And there are many other companies, both from America and other countries, that participate in this project. STEM uses an established industry standard solution. Eclipse Equinox is the reference implementation of OSGI based on Java. And all STEM components can be dynamically loaded as bundles or plugins. There are viewers like the map view, Google Earth, Google Maps, NASA, etc. There are disease models, population models, various data sets. Users can create their own scenarios or use out-of-the-box scenarios, and they can easily combine, manage, and partition plugins across various domains. That makes STEM way extensible, flexible, and highly reusable. STEM is based on epidemiological compartment models, either a more complete version that also takes into consideration that people can be exposed to an infection but not yet infectious themselves. So they carry the disease, but they are not able to infect others, or a simplified version where this is not taken into consideration. STEM treats the whole world basically as a big graph. The edges with labels and decorators. That way it makes it easy to build one model and extend it with another model to reuse the existing model without having to create everything from scratch. Existing plugins define transportation systems the population of a vast majority of the world, including 244 countries and other areas. There are many vectors of infectious diseases. Here, the example of the human flu and the swine flu that then mutate and mix. And we also saw other examples in the past. Many of the most lethal and dangerous diseases, including HIV, also are believed to have spread from other animals like mammals onto humans. And although it's not yet fully confirmed, but there's also a theory that the novel coronavirus may have spread from other animals in China and then started to infect humans. STEM has a core integration engine that allows you to choose between the finite difference solver, which is very fast and good for demos, a more complex solver called Runge-Kutta-Fehlberg, or RKF45, using adaptive integration. It allows you to adapt the step size. It's efficient and accurate. It's synchronized across multiple threads, and computational errors are estimated and controlled appropriately. There's also another one using the Apache Commons Math project, Dorman Prince 54, or you can create your own user-contributed solvers. STEM effectively allows you to run a simulation even on your own laptop if it's powerful enough. STEM includes global air travel models based on data by the FAA. Every commercial US airport is included, as well as approximately 80% of all other airports around the world. The US counties and states are modeled in several ways. The common border edges, interstate highway or train, although the latter is not so important in the US as it may be in other countries, and of course air travel. There are several ways of modeling interventions. The data is based on HL7 exchange, weather information, or air traffic data. And then STEM includes a framework of various predicates, modifiers, and triggers. So, of course, the most commonly known countermeasure nowadays, also for COVID-19, is wear a mask. Where that doesn't help, or a country or a state is highly affected, there can be air travel bans. Vaccines, as soon as they are available and safe and tested. And you can also combine that. For example, wearing masks and flight bans, which allows to further reduce the spread of the infection. And various combinations of these and additional countermeasures. STEM includes a graphical model creator, allowing you to create the disease models by drag and drop. And that brings us to the next part, where Seko and Oliver will tell you about disease models.
Now that we've had a brief intro into STEM, let's actually talk a little bit more about what we mean when we say disease models. So depending on what your background is, the term model may have many meanings, but in this work we specifically refer to mathematical models. Models allow us to generate a representation or an understanding of the underlying phenomena. In this case, what happens with the disease. So for us, the mathematics provides a formulation. We can use this formulation to solve the problem, and then once we have those solutions, we can keep driving. So we can develop an interpretation of what is happening based on the solution. We can check that interpretation with well-known facts, and then we can make changes to the assumptions that we make, or maybe we can change something about how the model represents what is happening in this real world, and then we can continue the cycle again. So fundamentally, models help us understand what's happening by providing a simplification of the real world process, and we can use this to better understand and iteratively gain increased understanding. Models can be empirical on one side, and on the other side they can be mechanistic. So what does this mean? Empirical being completely data-driven, and mechanistic meaning that there are either some sort of domain expertise, which is used to define exactly how all elements of that model works. So one paradigm that we can use to capture the relationship between the many different types of mathematical models is the concept of saying, on one extent, you can have a black box, and we will say that approaches like neural networks, which are very popular these days, they constitute black box models. In essence, all of the parameters that are used to do the mapping between whatever that model's input and whatever the model's output, it's very difficult to understand the relationship between the two. On the other extent is what we talk about as the mechanistic model. So in essence, some sort, like let's say differential equations that are well understood from a biological perspective could be used to define the relationship between the input to the model and the output to the model. But the goal in all of these cases is that we would like the models to, as best as possible, approximate the relationship or the mapping between input and output. When we consider what's provided for use with STEM, we're specifically focused on spatiotemporal compartmental models. So there's a notion that these compartmental models can incorporate information about time and space. There are, if you've taken a look at the STEM wiki already, or hopefully you'll do so immediately after listening to this presentation, you'll find that there are multiple population models. There are also multiple zoonotic models, in essence, models that capture the relationship between animals and humans, for example, to have different types of model transmission. But this concept of space is really cool because now you can actually capture the relationship between an infection coming from the result of an individual traveling from a location nearby, let's say a neighboring region. Right? The obligatory differential equations, you know that we're talking about epidemiological models, so we must talk about the equations. These equations define the math, the functionality. So concepts like transmission rate, concepts like mortality rate, all of these are encoded into these differential equations. And you'll see in a little bit how those are then used to define this mathematical model implementation within STEM. In STEM, graphs sit conceptually at a lower level right under models. But for STEM, everything is a graph. So it's an abstraction which allows the concepts of countries or highway systems to be mapped. So for example, there are even graphs that might capture the flight of birds if you're interested in the zoonotic disease that is the vector is birds. So graphs are an abstraction which underlie exactly how STEM is able to capture these varied relationships and these the plurality of diseases, which are other things, because you'll probably find out that STEM is not only able to be applied with infectious diseases. Right. So on the STEM wiki, there are currently 3 COVID-19 models. The differences between these models are rooted in the compartments which are available, and also the kinds of assumptions about what is happening in the particular model. So for example, the first model, the SAIR model, assumes that basically the population moves from being susceptible to being, in essence, you can call this as pre-symptomatic, to infected, and then either the unfortunate case of death or recovery. And in this particular case, this model also allows someone who is recovered to then become susceptible again at some time in the future. The model that we'll focus on for the rest of this demo is the SACIR model. And in this case, you have pre-symptomatic and asymptomatic cases. So it's a little bit more complex, a richer set of assumptions on what is happening in the population. But it's one of many different framings of what is happening from a COVID-19 perspective. Digging in a little deeper, there are many parameters in these models, and it's a process to determine what these parameters ought to be. STEM provides support to even calibrate the models to data, allowing some of these parameters to be learned. But then, as a modeler, you have the ability to interrogate or investigate and actually try to define parameters yourself. And some more of this will be discussed in the demos.
And I'll use this part of the presentation to run through a demonstration of the STEM 4 SACIR COVID model. So the model, as detailed previously, is contained on the STEM wiki pages as an example. So what's contained here are the associated download files that you can take from the wiki. These consist of the COVID-19 compartmental model, so the SACIR compartments, and the defined transitions between those compartments. Importantly, in the SACIR model, we would like to look closely at the transitions between the asymptomatic and the total number of cases. So we have a case reporting rate that distinguishes transmission between the A and the C compartments, which share a common transmission rate. So this COVID-19 model, the SACR model, has been imported into a single node scenario example, which I'll load up here, containing the disease model, the model we've just been through. This model, in the properties viewer below, we can see the specified parameters for the model, and for this example, it's not a specific geographic location, just using STEM's standard human population model and a single node graph definition. Within the model, also this scenario, there's a sequencer which defines the time period for the simulation run between the 2nd of March and 1st of November, and data is initialized from this recorded simulations file that contains the initializers for the compartment values, so the SACIR compartments, along with the total population count. Interventions in STEM are defined as triggers. So this intervention trigger within the single node scenario consists of 2 parts, a predicate and a modifier. The predicate defining the timing of the trigger or intervention. So this will be implemented after 20 days and lifted after 180 days in this instance, and the modifier defines the change in one of the model properties. So in this case, the transmission rate parameter, 0.26. If we go back to the model properties and look at the default transmission rate, we can see it's 0.4. So this social distancing intervention implemented after 20 days will have the effect of reducing the model transmission rate and then returning it to 0.4 after 180 days when it's lifted. For this scenario, the solver used is specified as the Duman print solver. So having been through all the components of the scenario file, we can now choose to run it. So here the above graph map view for STEM is not so useful for our purposes as we're not looking at multiple geographic locations, just a single node, so a single square in the grid. We won't see much of interest above, but the time series view on the bottom right will provide information on the compartment numbers as the simulation proceeds. So slowing down how are stepping through the simulation, we can see as the simulation progresses, the transition between the compartments and numbers across time. The most significant compartments here being the susceptible S compartment in blue, the recovered population in green, and the asymptomatic population here in orange. So we can see at initialization there's a reasonably large recovered population, so underlying immunity in the population, and then a significant number of asymptomatic individuals that are being modeled. In this case, the number of susceptibles decreases to a point, and then we see the immunity decay rate defined to increase the number of susceptible individuals, at which point those who are recovered are also decreasing, and then the number of asymptomatic infections starts to increase again after 180 days when the social distancing intervention is lifted. Okay, so having been through a single scenario file, we can now look at how we could extend that to multiple runs of a scenario file to try to better determine an epidemiological parameter of our model, so calibrate our model to observed incidence. This experiment looks at the single parameter of the case reporting rate, so the proportions of infections that are split between the C and the A compartments, so the asymptomatic individuals and the symptomatic individuals. So we have a single modifiable parameter of the case reporting rate. For the purposes of the demonstration, we'll set this to 0.05, so perturb the parameter slightly more for the purposes of visualizing results. And the automated experiment will use what's determined here as a simple error function. Practically, this is the normalized mean squared error between the instance compartment of the model and reference instance data that we have within the recorded simulations directory, which we're aiming to calibrate against. The selection of case reporting rate values and exploration of this parameter space will be done with the STEM simplex algorithm, which it will look to explore optimal parameter values against the error function that we've defined on the instance compartment. So again, we can run this automated experiment, which will load an automatic experiment view, and each of these runs defines an entire scenario run that we went through previously, and the associated normalized mean squared error from that run on the instance reference data. So the simplex algorithm in this case is reducing the error in the case reporting rate best estimate, but also continuing to explore slightly and perturb the value such that we start to converge on a best possible estimate given the data in the model. We can see here the projection, the model projection in green based on the latest case reporting rate estimate against the reference data, so the corresponding fit, and we can see where the remaining error comes from, also across time in this view from the fit. And so current values from the runs also can be viewed in the tab. If we select using the best estimate value, we can actually reinitialize our exploration of case reporting rate around this best estimate if we then select restart. And the experiment has been restarted and run quick 27 times around that value. When we go back and we see that we have a slight perturbation in our best estimate that we could continue to see if there's any significant change in. Okay, thank you. I think that confirms, concludes this part of the demonstration and presentation, and we'll move on to the next part.
Welcome to STEM 5 session. I'm Ahmed Swed, a senior software developer and part of STEM community since 2 years. Currently, I'm supporting the community in migrating STEM to the web, trying to provide a scalable enterprise cloud-native solution. By this migration, we have created a modern web application and tried our best to keep the same user experience of the original desktop version. In background, you see the current desktop version, and in front there is 2 snapshots taken of the web application. This web application is one of multiple components working together to provide the cloud solution of STEM. This will give a better performance and more scalable application. And of course, if we run multiple instances of each component, this will give us more scalability and better performance. If you look to the original design of STEM, you find that it's composed of multiple artifacts working in an OSGI container. Some of them are serving the user interface, and the other are serving the backend, which is the core of STEM. And the cohesion between these 2 parts or tier is very low. And the challenge was how we can keep the backend artifacts as is and keep their nature as an OSGI artifacts and try to run them in a GEE container. And also how we can deploy this final jar file in any native cloud provider. By this way, we keep the original OSGI nature of the core STEM artifacts, and we encapsulate them to be part of cloud technologies. These save our time, that we don't have to rewrite these artifacts again to be able to run in any cloud provider. The only part what we rewrite is the user interface. But the other parts we are working on them, that we encapsulate them to be able to run inside a cloud provider. Here you can see the initial design of the solution, where we have some central component like the service registry. We are using Eureka for that, and the configuration server, where any STEM microservice, when it starts, it communicates first to this config server to download the configuration, and then it can start. Also, we are using Sol as API gateway and Kafka as message broker. And here you can see the core component of STEM. Now let's move and show the solution in the development environment. Here you can see that I have started two central components, the config server, which is managing the configuration which are stored on GitLab. And also here you can see that the discovery service is started on port 9000. If I click here, then you see Eureka, and that we have two microservices started. Now we have the core and the user interface microservice. If I click here, then I have to authenticate myself. And here we are. This is the dashboard of STEM. If we go to the model builder, you can see that we have already some project defined here. This is scenarios, this is the models and the graphs. And as you see, this design, we tried to keep the original design of STEM, but in modern way. This is the same, almost the same design of STEM. And here you can see the navigation bar as a sidebar. And if we go to scenarios, you can choose to create scenario. Also the model. It is the graph. You can choose what project you want to create the graph in. What's the name of the graph? Here you see that the design is changing in time to your need. At the end, I would like to thank you for joining us.